The next section is about lipids, so that's the next kind of macromolecule we're going to learn about. And so lipids are actually the only one that actually don't form polymers, and we'll talk about why that is. But the way that we characterize lipids is based on the fact that they do not mix with water. So they are generally, as a class, hydrophobic, and so they do not have an affinity for water. And this is because of their molecular structure, which we'll also talk about. So remember, structure, fitting, function, and we'll see why that is. We have a lot of different kinds, but the kinds that we're going to talk about are fats, phospholipids, and steroids. Oh, and they're hydrophobic because they consist mostly of hydrocarbons, so carbons bonded to hydrogen, which there's no difference in electronegativity there, so hydrocarbons are very nonpolar. So the fats that are made of hydrocarbons are nonpolar, so they don't mix with polar water. So the first one, and what you guys maybe remember as being lipids, is fats. And fats are made of two smaller molecules, which are glycerol and fatty acids. Glycerol is an alcohol, and it has 3 hydroxyl groups on it. And a fatty acid is a really, really long hydrocarbon, which is 16 to 18 carbons in length. And there's 3 fatty acids attached to every glycerol. And the fatty acid is the really, really nonpolar part of the fat because it's a straight up hydrocarbon chain. No polarity, nothing. It's very nonpolar, so it doesn't mix with water. This is why, if you think about fatty foods or like salad dressing, why the oil doesn't mix in with the water, because of the nonpolar hydrocarbon tails. So here we can see the structure of a fat. So here's our glycerol right here. It has 3 hydroxyl groups, and here's our fatty acid chain. This fatty acid chain comes, and the hydroxyl right here goes with this oxygen. They leave and form water in a dehydration reaction, and then they're bonded. This fatty acid is bonded to this glycerol, and that's what's called an ester linkage. So we're going to talk about different kinds of bonds for each macromolecule. So for fats, it's ester linkage. And the way that I always remember this, because it's what my high school biology teacher told me, is think of Esther as being this really fat woman, and then that's how you remember it. Ester linkages is what bonds fats together. So we see 3 hydroxyls on this glycerol, so we have 3 fatty acids bonded to 3 types of ester linkages. So this right here is what's called a triacylglycerol, because there's 3 fatty acids attached to this glycerol. We also can call this triglyceride, which you may have heard of before. And the fatty acids can be the same or they can be different. So here we have what looks like 2 of the same fatty acids and 1 different in the middle. And here we see again water or hydrogen of the glycerol, hydroxide of the fatty acid, leave together, you lose a molecule of water in a dehydration reaction. So we talked about this. So fats separate from water because water molecules form hydrogen bonds with each other and exclude the fats. So it's not that fats don't want to be near water. They're not actually hydrophobic, afraid of the water. It's just that water sticks so strongly together because of its hydrogen bonds that the water is excluding the fat. So it's not the fat being too cool for the water and not wanting to be a part of it. It's the water not wanting the fat around, so they push it away. So not only do fatty acids vary in the number of carbons in their chain, they also can vary greatly based on the number and locations of double bonds between the carbons in the carbon chain. So you guys have probably heard of saturated and unsaturated fats, and what that means is how many how many hydrogens are attached to each carbon chain. So here, this carbon chain, so each of these bends stands for a carbon, and you see there's no double bonds. So if there were a double bond, that means that there's fewer hydrogens because those bonds are being taken up by a double bond between the carbon. So in this carbon chain, so this carbon right here is attached to 1 carbon right here and 1 carbon right here and 2 hydrogens right there. So it's saturated. It has as many hydrogens as possible. And that's what a saturated fat is versus an unsaturated fat, which right here, there's a double bond. So this carbon right here is attached to this carbon and has 2 bonds to this carbon, so it can only have 1 hydrogen attached right there. So it's unsaturated. It does not have as many double bonds as it possibly could. That's what saturated and unsaturated means. It means saturated with hydrogens. So the difference in these in food is why it's healthy versus not healthy. So saturated fats are solid at room temperature because all of these guys are totally straight. They're basically completely linear because they're unsaturated, or they're saturated. They have as many hydrogens as possible. They form a straight line. So when they're near each other, they can pack really tightly and become a solid at room temperature. So think of it like a box of pencils. If you throw a lot of pencils in all in one direction, they can form really tightly to each other, and there's not going to be a problem. There's not going to be space between them, so it would be a solid. And these are really bad for you because they form solids inside your arteries and block your blood flow. So that's why saturated fats are bad for you. Unsaturated fats over here, when we have a double bond, we get a kink in the chain. So it's linear. These two are linear because they're saturated. Then we get down here and there's a double bond and it forms a kink in the chain because of differing bond angles. So now, rather than trying to pack a bunch of pencils into a box, now think of it with a bunch of pencils and a couple of crazy straws thrown in there, like windy, crazy straws. And so when that happens, now we can't pack them in as tightly. We can't get as many in there, and it's not a solid at room temperature. So these are things like olive oil. And these are not nearly as bad for you because they don't form blockages in your arteries because they don't form solids inside your arteries. So that's the main difference between saturated and unsaturated fats. Saturated fats tend to come from animals, like butter is an animal fat, comes from milk, whereas olive oil or vegetable oil, anything like that comes from vegetables. So unsaturated fats tend to come from vegetables, and saturated fats tend to come from animals. Oh, if you've ever heard of the term hydrogenated. Oh, also fish fat is unsaturated. Okay, so hydrogenation, if you've ever heard of anything being hydrogenated, is the process of adding extra hydrogens to an unsaturated bond. So right here, if I take this and I throw extra hydrogens in there, get rid of that double bond, now it's suddenly saturated. So that's what hydrogenation is adding the extra hydrogens to make it saturated. And we do this a lot with like vegetable oil. You can hydrogenate vegetable oil and then it becomes a solid, like shortening, and to make it a solid at room temperature. And then this creates saturated fats with trans double bonds. And so trans fats are what's really bad for you, and because of the way that the double bonds are. So hydrogenation is the process of turning unsaturated fats to saturated fats. And then there's certain unsaturated fatty acids that our bodies don't make, but are really important in our diet. And so you've probably heard of these like in the news in regards to nutrition, such as omega-3 fatty acids, and we need these, and so we need to get them from someplace else because our body doesn't make them. And these are things they're required for normal growth, and they're thought to provide protection against cardiovascular disease. So like salmon and almonds and avocado and things like that, those have fats that are good for you, like this right here. And the main function of fat is energy storage. So think of it this way: if you eat way too much, your body's not just going to get rid of all that extra food you put into it, it's going to store it as fat. That way, in case you don't get a chance to eat later, it can use it. So the main function of fat is energy storage. And humans store their energy in what's called adipose cells. Those are fat cells inside the human body. And not only do they store energy, they also provide cushioning for vital organs and insulate the body. So you have fat around most of your vital organs because that way, if you were to get hit or fall down or anything like that, if you were to have trauma to your body, your vital organs would be protected because that's very important. And they also insulate the body. So in humans, we go inside and we wear clothes and things like that. So this isn't as big of a key, but think about mammals that live in the water, like whales and things like that. They have very, very thick layers of blubber that protects them in the winter because it insulates the body. The next type of lipid is what's called a phospholipid, and this is because it has a phosphate attached to it. What it looks like is this. So we have, instead of a third fatty acid being attached, we have a phosphate group. So we have two fatty acids and a phosphate group attached. And these are a big part of the cell membrane. and we'll talk about why that is, but the phosphate head is hydrophilic. It is polar because it has this charge right here, this negative charge, so it can form hydrogen bonds with water, whereas the fatty acid tails are still nonpolar. So when we add these to water, they form a phospholipid bilayer, like we have right here. So all of the hydrophobic fatty acid tails fold inward to stay away from the water, and the phosphate heads face outward because they are charged and they like water. And this phospholipid bilayer is what all of our cell membranes are made of. So structure, fitting, function again. So we need our cell membranes to protect the inside of our cells from the outside, and if they liked water, then that would be a really big problem because then they would dissolve and we wouldn't have a cell membrane. So the fact that the inside is hydrophobic allows for this phospholipid bilayer to form and to protect the inside of our cells from the outside. That's an example of structure, fitting, function. And phospholipids are the main component of all cell membranes. All right, so the last group we're going to talk about are steroids. So steroids are lipids, and they are characterized by a carbon skeleton consisting of 4 fused rings. And so they have a little bit of a different structure than glycerols, than fats and phospholipids. But they are there's a lot of different kinds of steroids. So one important one is cholesterol, which is found in our cell membranes. So it's really good for you. You need cholesterol because it adds to the fluidity of your cell membranes, allows your cells to be flexible, but too much of it can also build up inside your arteries and cause blockages, just like saturated fatty acids. Can lead to cardiovascular disease, just like we said. And so this is what a steroid looks like. This is cholesterol. So there's 4 fused carbon rings, and over here we have a nonpolar side chain. So all of these are very nonpolar because you see when you just have carbons and hydrogens, there's basically no polarity. We have the hydroxyl group down here, but for the most part, everything is carbons and hydrogens. No side groups, no nothing to make it polar and have an affinity for water. So it's very nonpolar. And that's the end of lipids.